Hi, welcome to Electrical Info YouTube channel. Subscribe our channel and share. Today we learn HV substation elements, graphic symbols, basics and connection schemes. Substation elements. High voltage substations are pretty complex to understand since they have a way to many elements and each element is complex for itself and it depends on many system parameters and other elements. This video will shed some light on these elements, their graphic presentation as well as their brief description and the most common substation connection schemes they usually appear. Note that described elements described are the main ones. There are many variations and combinations of equipment, for example switch disconnectors or circuit breakers, combined CTs and VTs into one, digital protection relays and so on. Nowadays, all these elements are getting more and more advanced and technically better, but the core base is the very same as they were 30 years ago. Working principles are the same. So, let's get into core substation elements. Next we learn about 1. Graphic symbols of substation elements. 2. Equipment in power substation. 1. Busbars. 2. Insulators. 3. Isolating switches, disconnectors. 4. Circuit breakers. 5. Power transformers. 6. Instrument transformers. 7. Current transformers, CTs. 8. Voltage transformer, VTs. 9. Protection relays. 10. Metering and indicating instruments. 11. Miscellaneous equipment. 12. Busbar arrangements in substations. 13. Single busbar system. 14. Single busbar system with sectionalization. 15. Double busbar system. Next we learn about graphic symbols of substation elements. Substations are usually presented using various elements, example, power transformers, circuit breakers, isolators, instrument transformers CTs, VTs etc., by their graphic symbols in the connection schemes. Symbols of the most important equipment in transformer substation are given below. Note that these symbols might not look the same depending on the standard applied, NEMA or ANSI. Next we learn about busbars. An electrical busbar is a metal strip or bar used to distribute electrical power to multiple electrical loads or devices. It is commonly used in electrical power distribution systems, where it serves as a central point for the connection of multiple electrical circuits. Busbars are typically made of copper or aluminum and are designed to handle high current loads. They can be shaped in a variety of ways, including rectangular, round, or hexagonal shapes, depending on the specific application and requirements. Bus bars can be found in a range of electrical systems, including switchgear, substations, and distribution boards. They provide a reliable and efficient means of distributing power throughout an electrical system, and their use can help to minimize voltage drops and reduce the likelihood of electrical faults or failures. In summary, electrical bus bars are an essential component in the distribution of electrical power in modern electrical systems, providing a reliable and efficient means of distributing power to multiple loads or devices. Next we learn about busbar symbols. Electrical busbar symbols are used in electrical diagrams and schematics to represent busbars in an electrical system. These symbols are standardized and commonly used in electrical engineering and design. There are several different symbols used to represent electrical busbars, depending on the specific application and the type of busbar being used. Some of the most common busbar symbols include straight busbar. This symbol is a simple straight line that represents a straight busbar. It is often used to show the location of a busbar in a larger electric Cal diagram. L-shaped busbar. This symbol is an L-shaped line that represents an L-shaped busbar. It is often used to show a busbar that turns at a right angle. T-shaped busbar. This symbol is a T-shaped line that represents a T-shaped busbar. It is often used to show a busbar that branches off in two directions. Three-phase busbar. This symbol is a set of three parallel lines that represent a three-phase busbar. It is often used in power distribution systems to show the connection of three-phase loads. Busbar with tap. This symbol is a line with a small perpendicular line coming off of it, representing a tap-off of the main busbar. It is often used to show a connection point for a specific load or device. In summary, electrical busbar symbols are standardized and commonly used in electrical diagrams and schematics to represent busbars in an electrical system. These symbols can represent different types of busbars and can provide valuable information about the configuration and layout of an electrical system. Next we learn about isolators. Electrical substation isolators, also known as disconnect switches or isolation switches, are critical components of electrical power systems. They are used to isolate different parts of a power system for maintenance or repair purposes, or to de-energize specific sections of the system during an emergency. Isolators are designed to operate under load conditions and provide a visible means of isolation. Isolators are typically installed at various points in a power system, including at the entry and exit points of transformers, transmission lines, and distribution lines. They are also installed at switching stations, switch yards, and substations, where they provide an additional level of safety and protection for personnel working on or near the power system. Isolators are available in various types, including vertical brake and horizontal brake. Vertical brake isolators are typically used for transmission lines, while horizontal brake isolators are used for distribution lines. Isolators are also available with different mounting arrangements, including pole-mounted, structure-mounted, and ground-mounted. The basic operation of an isolator involves opening and closing of contacts to isolate or connect a part of the power system. When the isolator is closed, the contacts are in contact with each other, and electricity can flow through the system. When the isolator is open, the contacts are separated, and the flow of electricity is interrupted. Isolators are critical components of electrical power systems, and their proper operation is essential for the safe and reliable operation of the power system. Regular maintenance and inspection of isolators are necessary to ensure their proper functioning and to prevent any potential hazards or accidents. Next we learn about isolators symbols. Electrical substation isolator symbols are graphical representations of isolators that are used in electrical system design and documentation. These symbols are standardized to ensure consistency in their use across different types of documents and engineering disciplines. The symbol for an isolator typically consists of a rectangular box with a diagonal line running through it. The diagonal line represents the isolation function of the isolator, with the contacts on either side of the line indicating the open or closed position of the isolator. The position of the diagonal line in the box indicates the direction of the isolator's operation. Isolator symbols are often accompanied by additional information to provide more details about the isolator, including its voltage rating, current rating, and any other relevant information. This information is typically provided in a table or a legend on the drawing or document. Isolator symbols can vary depending on the type and application of the isolator. For example, a vertical brake isolator may have a different symbol than a horizontal brake isolator. Similarly, the symbol for an isolator used in a distribution system may be different from the one used in a transmission system. The use of standardized isolator symbols in electrical system design and documentation is essential to ensure clear communication and understanding between engineers, designers, and technicians working on the power system. It helps to reduce errors, increase efficiency, and promote safety in the design and operation of electrical power systems. Next we learn about isolating switch with earth blade. An isolating switch with an earth blade, also known as a disconnect switch, is a device used in electrical substations to isolate or disconnect a part of the electrical network for maintenance, repair, or emergency operations. The switch consists of a set of blades or contacts that can be moved to connect or disconnect electrical circuits. In the case of an isolating switch with an earth blade, there is an additional blade that is used to ground the circuit being disconnected. This earth blade provides a path for the electrical energy to be safely discharged to the ground, reducing the risk of electric shock and protecting the equipment from damage. Isolating switches are designed to be operated manually or automatically and are typically used in conjunction with circuit breakers and other protective devices to ensure the safety and reliability of the electrical network. They are also used to isolate equipment for maintenance or repair work, allowing technicians to work safely on the electrical system without the risk of electrical shock. Overall, the isolating switch with an earth blade plays an important role in ensuring the safety and reliability of the electrical power grid, and is an essential component of any electrical substation. Next we learn about Isolating switch with earth blade symbol. In electrical engineering, symbols are used to represent different components and devices used in electrical circuits and systems. Isolating switches with earth blades are commonly used in electrical substations, and they have a specific symbol that is used to represent them in electrical diagrams and drawings. The symbol for an isolating switch with an earth blade consists of a rectangular box with a vertical line in the middle. The vertical line represents the switch's blade or contact, which can be moved to connect or disconnect electrical circuits. In addition to the vertical line, there is a horizontal line that is perpendicular to the vertical line, which represents the earth blade or ground blade. The earth blade is typically located at the bottom of the switch, and it is connected to the ground or earth. The symbol for the isolating switch with an earth blade may also include additional details, such as the switch's voltage and current rating, as well as any other relevant information, such as the switch's position or status. Electrical engineers and technicians use these symbols to create electrical diagrams and drawings that accurately represent the electrical circuits and systems they are working on. The symbols make it easy to identify and locate different components and devices, and they help ensure that electrical systems are designed and installed correctly, efficiently, and safely. Next we learn about air blast circuit breaker. An air blast circuit breaker is a type of electrical switchgear used to protect electrical equipment from damage caused by overcurrents or short circuits. It operates by interrupting the electrical current flowing through a circuit using a high-pressure blast of compressed air. The main components of an air blast circuit breaker include a set of contacts, an air compressor or pressure vessel, a control valve, and an air nozzle. When a fault occurs in the circuit, the contacts of the circuit breaker are opened, and a high-pressure blast of compressed air is released from the air nozzle, extinguishing the arc that forms between the contacts. Air blast circuit breakers are typically used in high-voltage substations and are designed to withstand high levels of electrical stress. They are known for their fast operating times, high reliability, and low maintenance requirements. One of the major advantages of air blast circuit breakers is their ability to interrupt high current levels, which makes them suitable for use in heavy-duty applications. They are also capable of interrupting capacitive currents, which can be challenging for other types of circuit breakers. In summary, air blast circuit breakers are a type of switchgear that uses a high-pressure blast of compressed air to interrupt the flow of electrical current in a circuit. They are commonly used in high-voltage substations and are known for their fast operating times, high reliability, and ability to interrupt high current levels. Next we learn about air blast circuit breaker symbol. The symbol for an air blast circuit breaker in an electrical substation is AR. Rectangular shape with two lines running horizontally through the middle. The lines represent the contacts of the circuit breaker. On either side of the contacts, there are two arrows pointing towards the center of the rectangle. These arrows represent the compressed air blast that is used to extinguish the arc. Above the rectangle, there is a small triangle pointing upwards. This triangle represents the direction of the airflow during the operation of the circuit breaker. Finally, on either side of the rectangle, there are two small circles with a horizontal line through them. These circles represent the air pressure gauge and the pressure relief valve that are used to monitor and control the compressed air supply. Overall, the symbol for an air blast circuit breaker in an electrical substation is designed to convey the key components and functions of the circuit breaker in a simple and intuitive manner. Next we learn about lightning arrestor. An electrical substation lightning arrestor, also known as a surge arrestor or a lightning protector, is a device designed to protect electrical substation equipment from lightning strikes and power surges. It is an essential component of any substation, as lightning strikes and surges can cause significant damage to electrical equipment, leading to outages and costly repairs. The lightning arrestor works by providing a low impedance path for the surge current to follow to ground. When a lightning strike or surge occurs, the arrestor conducts the surge current to ground, diverting it away from the equipment it is designed to protect. This helps to prevent damage to the equipment and ensures that it continues to function as intended. The lightning arrestor typically consists of a metal oxide varistor, MOV, or a gas discharge tube, GDT, connected in parallel with the equipment being protected. When a surge or lightning strike occurs, the MOV or GDT conducts the surge current to ground, effectively clamping the voltage and limiting the amount of energy that reaches the protected equipment. It is important to note that lightning arresters are not a foolproof solution, and they can still fail if subjected to a particularly large surge or if they are not properly installed or maintained. For this reason, it is essential that lightning arresters be inspected and tested regularly to ensure they are functioning correctly and that any defects or damage be repaired promptly. Lightning arrestor symbols. In electrical substation design and documentation, lightning arresters are typically represented by specific symbols. SA symbols are used to indicate the location and type of lightning arrestor installed in the substation. The most commonly used symbol for a lightning arrestor is a zigzag line with a vertical arrow pointing downward. This symbol represents the electrical connection of the lightning arrestor to the ground. In addition to the basic lightning arrestor symbol, there are also variations that indicate the specific type of lightning arrestor being used. For example, a symbol with a circle or diamond inside the zigzag line may indicate a metal oxide varistor, MOV, lightning arrestor, while a symbol with a line connecting two zigzag lines may represent a distribution class lightning arrestor. Symbols may also be used to indicate the location of lightning arrestors within the substation. For example, a symbol with a diagonal line may represent a lightning arrestor installed on an overhead transmission line, while a symbol with a horizontal line may represent a lightning arrestor installed on a substation bus or other electrical equipment. Overall, the use of standardized symbols for lightning arrestors helps ensure clear and consistent communication between electrical engineers, technicians, and other professionals involved in the design and operation of electrical substations. Next we learn about arcing horn. An arcing horn is an important component of electrical substations. It is used to control and prevent dangerous electrical arcing that can occur when high-voltage power lines are switched on or off. An arcing horn is essentially a metal structure that is mounted on the top of high-voltage equipment, such as a transformer or circuit breaker. It is designed to provide a path for the electrical current to jump from the equipment to the surrounding air. This is important because when high-voltage equipment is switched on or off, a surge of electrical energy is produced that can cause arcing between the equipment and nearby objects, such as other pieces of equipment or the ground. This arcing can be dangerous, leading to equipment damage, power outages, and even injury or death to personnel. The arcing horn provides a controlled path for the electrical current to jump from the equipment to the air, where it is safely dissipated. The design of the horn is critical to its effectiveness, as it must be carefully sized and positioned to ensure that it can handle the electrical energy produced during switching without causing damage or arcing to nearby objects. In summary, the arcing horn is a crucial component of electrical substations that helps to control and prevent dangerous electrical arcing that can occur during switching operations. Its design and positioning must be carefully considered to ensure safe and effective operation. Next we learn about arcing horn symbols. The symbol for an arcing horn in electrical diagrams is a simple geometric shape that represents the physical structure of the component. The symbol consists of a triangle with a flat base, which is oriented upward and connected to a straight line that represents the mounting base or bracket. The triangle portion of the symbol represents the shape of the arcing horn, which is typically a triangular or conical structure made of metal. The flat base of the triangle represents the broad end of the horn, which is where the electrical current is discharged into the surrounding air. The straight line portion of the symbol represents the mounting bracket or base that attaches the arcing horn to the high-voltage equipment. The bracket is usually made of metal and designed to securely hold the horn in place, while also providing a path for the electrical current to flow into the horn and then discharge into the air. In electrical diagrams, the arcing horn symbol is typically used in conjunction with other symbols for high-voltage equipment, such as transformers and circuit breakers, to indicate the presence of this important safety component. By including the arcing horn symbol in the diagram, electrical engineers and technicians can ensure that the proper safety measures are taken to prevent dangerous electrical arcing during switching operations. Next we learn about current transformer. An electrical substation current transformer, CT, is a device used in electrical power systems to measure electric current. It is also known as an instrument transformer, which means it is a type of transformer that is used to measure or provide a reduced value of a high voltage or high current signal. The current transformer operates on the principle of electromagnetic induction, where a conductor carrying an alternating current, AC, generates a magnetic field around it. The CT is designed in such a way that the conductor carrying the high current passes through the center of the transformer, which creates a magnetic field proportional to the current. The CT has a primary winding, which is connected in series with the high voltage circuit, and a secondary winding, which is connected to a measuring instrument or a protective relay. The secondary winding of the CT is designed to provide a reduced current proportional to the primary current, which can be easily measured by the measuring instrument or protective relay. The current ratio of the CT is determined by the number of turns in the primary and secondary windings. Next we learn about current transformer symbols. In electrical diagrams, electrical substation current transformer, circuit T, symbols are used to represent the presence of current transformers in the electrical power system. These symbols are standardized to ensure consistency and clarity in electrical diagrams. The most commonly used symbol for a CT is a circle with a cross inside, as shown above. The circle represents the core of the transformer, while the cross inside the circle represents the primary winding of the cord. The secondary winding is not shown in the symbol because it is usually connected externally to a measuring instrument or a protective relay. The current transformer symbol is typically accompanied by a label indicating the CT ratio, which is the ratio of the primary current to the secondary current. For example, a label of 1000 fifths indicates that the CT has a primary current rating of 1000 amps and a secondary current rating of 5 amps. Next we learn about three-phase power transformer. A three-phase power transformer is a crucial component in electrical substations. It is used to step up or step down the voltage of the incoming power to the desired level before it is distributed to the load. Three-phase power transformers are highly efficient, reliable, and cost-effective in transmitting power over long distances. The construction of a three-phase transformer consists of three separate single-phase transformers that share a common core. Each single-phase transformer has its primary and secondary windings wound on the same core. The three windings are arranged in such a way that they are electrically and magnetically isolated from each other. In three-phase transformers, the primary windings are usually connected in either a delta or a star configuration, while the secondary windings are connected in the opposite configuration to provide the desired output voltage. The delta connection provides a higher output voltage than the star connection. Three-phase transformers are represented in electrical substation diagrams using standard symbols. The most commonly used symbol is a three-legged core with three sets of primary and secondary windings. Next we learn about three-phase power transformer symbols. Three-phase power transformers are commonly used in electrical substations for stepping up or stepping down the voltage of incoming power. They are represented in substation diagrams using standard symbols. The symbol for a three-phase power transformer consists of three legs, representing the three-phase windings, and two or three winding symbols, representing the primary and secondary windings. The number of winding symbols depends on the type of connection used for the transformer. The primary winding symbols are connected to the high-voltage power source, and the secondary winding symbols are connected to the load. The transformer symbol may also include additional markings such as the voltage and current ratings, tap positions, and other relevant data. Next we learn about capacitive voltage transformer. A capacitive voltage transformer, CVT, is an electrical device used in high-voltage substations to measure the voltage of the power lines. It works on the principle of electrostatic coupling between the primary and secondary windings. The primary winding of the CVT is connected across the high-voltage line, and the secondary winding is connected to the measuring instrument. CVTs are designed to provide a highly accurate voltage measurement, even under high transient conditions. They are widely used in power systems for protection and control purposes. The basic construction of a CVT includes a high-voltage capacitor, which forms the primary winding, and a low-voltage capacitor, which forms the secondary winding. The high-voltage capacitor is usually a single unit, while the low-voltage capacitor consists of several capacitors connected in series or parallel. CVTs are preferred over traditional voltage transformers because they provide a more accurate voltage measurement, especially under high transient conditions. They are also more compact, lighter in weight, and require less maintenance compared to conventional transformers. However, CVTs are more expensive than traditional voltage transformers and can be sensitive to environmental factors such as temperature and humidity. It is, therefore, important to ensure that they are installed and operated correctly to ensure their long-term reliability and accuracy. Next we learn about capacitive voltage transformer symbols. In electrical substation diagrams and schematics, capacitive voltage transformers, CVTs, are represented by specific symbols to simplify their identification and interpretation. The commonly used symbol for CVTs is a circle with two curved lines inside, as shown above. The circle in the center represents the high-voltage capacitor, and the two curved lines represent the low-voltage capacitors connected in series or parallel to form the secondary winding. The lines protruding from the symbol represent the connection points for the primary and secondary windings. Sometimes, the symbol may also include a small arrow indicating the direction of voltage measurement or a number indicating the voltage ratio of the CVT. The voltage ratio indicates the relationship between the voltage applied to the primary winding and the voltage measured at the secondary winding. It is essential to understand and interpret these symbols correctly to ensure proper installation, maintenance, and troubleshooting of CVTs in electrical substations. Next we learn about potential transformer. Potential transformer, PT, also known as a voltage transformer, VT, is an instrument transformer used in electrical power systems to step down high voltages to safer, measurable levels for protection and measurement purposes. PTs are commonly used in electrical substations, switchyards, and generating stations to provide accurate voltage measurements for protective relaying and metering applications. The construction of a PT consists of a primary winding connected in parallel with the high-voltage circuit and a secondary winding connected in series with the low-voltage circuit. The number of turns in the secondary winding is much greater than the primary winding, and the turns ratio determines the voltage transformation ratio. The PT's primary winding is designed to withstand high voltages, and the secondary winding is designed to produce a lower voltage, typically 120 or 240 volts. PTs are classified into two types based on their application: metering PTs and protective PTs. 1. Metering PTs. Metering PTs are used to provide accurate voltage measurements for metering and billing purposes. They have high accuracy and are designed to operate at rated voltage continuously. They have a low burden and are used to measure the voltage across the load. 2. Protective PTs. Protective PTs are used to provide voltage measurements for protective relaying and control purposes. They are designed to withstand high voltages during fault conditions and provide accurate voltage measurements. They have a high burden and are used to measure the voltage across the protective relaying and control equipment. PTs are represented in S/UB station diagrams using standard symbols. The most commonly used symbol for a potential transformer consists of a circle with two lines on either side, as shown above. Next we learn about oil circuit breaker. An oil circuit breaker, OCB, is a type of electrical switchgear used to protect and control electrical power systems. It is commonly used in high-voltage substations, where it functions as a part of the protection system for electrical transformers and other important equipment. The OCB operates by using oil as an insulating and arc-quenching medium. When a fault occurs in the power system, the OCB interrupts the electrical current by creating a high-impedance arc path between two contacts. This arc is then extinguished by the oil, which cools and absorbs the heat generated by the arc. The OCB also has mechanisms to control the arc and ensure that it is extinguished quickly and safely. OCBs have several advantages over other types of circuit breakers. They are highly reliable and can withstand high voltages and currents, making them ideal for use in high-power transmission systems. They are also relatively inexpensive compared to other types of switchgear. However, OCBs also have some disadvantages. They require regular maintenance, including oil sampling and testing, to ensure that the oil is still effective as an insulating and arc-quenching medium. They are also environmentally unfriendly due to the use of oil, which can leak and cause pollution. Overall, OCBs are an important part of modern electrical power systems, and they provide reliable protection and control for critical equipment in high-voltage substations. Next we learn about auxiliary transformer. An electrical substation is a critical component of an electrical power system, and it plays an important role in ensuring that electricity is delivered efficiently and safely to end users. One key component of a substation is the auxiliary transformer, which is used to power various auxiliary equipment and control circuits in the substation. An auxiliary transformer is a type of transformer that is designed to provide a low voltage, high current output to power auxiliary equipment and control circuits in a substation. This includes things like lights, fans, pumps, and other devices that are used to operate and maintain the substation. The auxiliary transformer is typically connected to the high voltage side of the main power transformer, and it steps down the voltage to a lower level that is suitable for powering the auxiliary equipment. The transformer is typically designed to operate at a frequency of 50 or 60 Hz, depending on the specific requirements of the substation. The design and specifications of an auxiliary transformer will vary depending on the specific needs of the substation. Factors such as the size of the substation, the types of equipment being powered, and the available power supply will all influence the design of the transformer. Overall, the auxiliary transformer is an important component of an electrical substation, and it plays a critical role in ensuring that the substation operates safely and efficiently. Next we learn about overcurrent relay. An overcurrent relay is a protective device used in electrical power systems to detect abnormal currents and to trip the associated circuit breakers to isolate the faulted equipment or system. The purpose of an overcurrent relay is to limit the duration of the fault and minimize damage to the equipment, as well as to protect personnel from electric shock. In an electrical substation, overcurrent relays are installed to protect the equipment in the substation, such as transformers, circuit breakers, and bus bars, from overcurrent conditions. Overcurrent conditions can be caused by short circuits, ground faults, or overloading. There are two main types of overcurrent relays used in electrical substations: instantaneous and time-delayed. Instantaneous overcurrent relays trip the associated circuit breakers immediately when the current exceeds a certain preset level, while time-delayed overcurrent relays have a time delay before tripping the circuit breaker to allow for temporary overloads. Overcurrent relays are typically designed to operate within a specific current range and have adjustable settings for current sensitivity, time delay, and trip curve. The trip curve is the graph that shows the relationship between the fault current magnitude and the time it takes for the relay to trip. In summary, overcurrent relays are an essential part of electrical substation protection schemes, providing reliable and fast protection against overcurrent conditions that can damage the equipment and cause power outages. Next we learn about overcurrent relay symbols. The symbol for an overcurrent relay is a rectangular box with diagonal lines passing through it, and a perpendicular line connected to the top or bottom of the box, depending on the type of relay. The diagonal lines represent the current flowing through the relay, while the perpendicular line represents the trip mechanism that trips the circuit breaker when the current exceeds a certain level. There are two main types of overcurrent relays: instantaneous and time-delayed. The symbol for an instantaneous overcurrent relay is a rectangular box with diagonal lines passing through it and a perpendicular line connected to the top of the box. The symbol for a time-delayed overcurrent relay is a rectangular box with diagonal lines passing through it and a perpendicular line connected to the bottom of the box. Additionally, the symbol may include letters and numbers that identify the type and characteristics of the relay, such as OCR for overcurrent relay and 50 for an ANSI standard overcurrent relay. Overall, the symbol of an overcurrent relay is a standardized representation used in electrical diagrams and schematics to indicate the presence and function of the protective device in an electrical system. Next we learn about earth fault relay. An electrical substation earth fault relay is a protective device used to detect ground faults in electrical power systems and to trip the associated circuit breakers to isolate the faulted equipment or system. Ground faults occur when a live conductor comes into contact with the ground or with a grounded object, causing a flow of current from the conductor to the ground. The earth fault relay detects the flow of current to ground and initiates a trip signal when the current exceeds a predetermined level. The purpose of the earth fault relay is to prevent damage to the equipment, reduce the duration of the fault, and protect personnel from electric shock. The earth fault relay can be connected in various configurations, such as in the neutral of a transformer, between the neutral and ground of a system, or in the ground return path of a system. The relay can also be designed to operate on different current levels and time delays, depending on the characteristics of the system and the type of equipment being protected. In an electrical substation, earth fault relays are typically used in conjunction with other protective devices, such as overcurrent relays and differential relays, to provide comprehensive protection against various fault conditions. The symbol for an earth fault relay in electrical diagrams and schematics is a rectangle with a diagonal line passing through it, with a perpendicular line connected to the top or bottom of the rectangle, depending on the type of relay. The diagonal line represents the current flowing through the relay, while the perpendicular line represents the trip mechanism that trips the circuit breaker when the fault is detected. Overall, the electrical substation earth fault relay is an essential component of the protection scheme for power systems, providing reliable and fast detection and isolation of ground faults to minimize equipment damage and ensure personnel safety. Next we learn about protection relays. The function of protective relays in a substation is to cause the prompt removal from service of any element of a power system when it suffers a short circuit, or when it starts to operate in any abnormal manner that might cause damage or otherwise interfere with the effective operation of the rest of the system. The relaying equipment is aided in this task by circuit breakers that are capable of disconnecting the faulty element when they are called upon to do so by the relaying equipment. They must also withstand closing in on such a short circuit and then interrupting it according to certain prescribed standards. Fusing is employed where protective relays and circuit breakers are not economically justifiable. Although the principal function of protective relaying is to mitigate the effects of short circuits, other abnormal operating conditions arise that also require the services of protective relaying. This is particularly true of generators and motors. A secondary function of protective relaying is to provide indication of the location and type of failure. Such data not only assist in expediting repair but also, by comparison with human observation and automatic oscillograph records, they provide means for analyzing the effectiveness of the fault prevention and mitigation features including the protective relaying itself. Next we learn about sensitivity, selectivity and speed. Sensitivity, selectivity and speed are terms commonly used to describe the functional characteristics of any protective relaying equipment. All of them are implied in the foregoing considerations of primary and backup relaying. Any relaying equipment must be sufficiently sensitive so that it will operate reliably, when required, under the actual condition that produces the least operating tendency. Note: it must be able to select between those conditions for which prompt operation is required and those for which no operation, or time delay operation, is required. And it must operate at the required speed. How well any protective relaying equipment fulfills each of these requirements must be known for each application. Note: the ultimate goal of protective relaying is to disconnect a faulty system element as quickly as possible. Sensitivity and selectivity are essential to assure that the proper circuit break. Next we learn about control and relay protection panels. Most protection relaying, metering, and control equipment is usually located in control and relay panels installed within the control house in a substation. There are many panel types as available to suit individual substation requirements. Next we learn about metering and indicating instruments. Every substation should have metering and indicating instruments, e.g. ammeters, voltmeters, energy meters etc., installed in its substation to maintain observation over the circuit quantities. Next we learn about miscellaneous equipment. In addition to above, there may be following equipment in a power substation: fuses, carrier current equipment, substation auxiliary supplies, batteries and other secondary equipment. Next we learn about busbar arrangements in substations. Bus bars are the important components in a substation. There are several busbar arrangements that can be used in a substation. The choice of a particular arrangement depends upon various factors such as system voltage, position of substation, degree of reliability, cost etc. The following are the important busbar arrangements used in substations. 1. Single busbar system. As the name suggests, it consists of a single busbar and all the incoming and outgoing lines are connected to it. The chief advantages of this type of arrangement are low initial cost, less maintenance and simple operation. However, the principal disadvantage of single busbar system is that if repair is to be done on the busbar or a fault occurs on the bus, there is a complete interruption of the supply. Note: this arrangement is not used for voltages exceeding 33 kV. The indoor 11 kV substations often use single busbar arrangement. Figure 7 shows single busbar arrangement in a substation. There are two 11 kV incoming lines connected to the busbar through circuit breakers and isolators. The two 400 volts outgoing lines are connected to the busbars through transformers, 11 kV, 400 volts, and circuit breakers. Next we learn about 2. Single busbar system with sectionalization. In this arrangement, the single busbar is divided into sections and load is equally distributed on all the sections. Any two sections of the busbar are connected by a circuit breaker and isolators. Two principal advantages are claimed for this arrangement. Note: firstly, if a fault occurs on any section of the bus, that section can be isolated without affecting the supply from other sections. Secondly, repairs and maintenance of any section of the busbar can be carried out by de-energizing that section only, eliminating the possibility of complete shutdown. This arrangement is used for voltages up to 33 kV. Figure 8 shows busbar with sectionalization where the bus has been divided into two sections. There are two 33 kV incoming lines connected to sections I and II as shown through circuit breaker and isolators. Each 11 kV outgoing line is connected to one section through transformer, 33/11 of a kV, and circuit breaker. Note: it is easy to see that each bus section behaves as a separate busbar. Next we learn about 3. Double busbar system. This system consists of two busbars, a main busbar and a spare busbar. Each busbar has the capacity to take up the entire substation load. The incoming and outgoing lines can be connected to either busbar with the help of a busbar coupler which consists of a circuit breaker and isolators. Ordinarily, the incoming and outgoing lines remain connected to the main busbar. Note: however, in case of repair of main busbar or fault occurring on it, the continuity of supply to the circuit can be maintained by transferring it to the spare busbar. For voltages exceeding 33 kV, duplicate busbar system is frequently used. Figure 9 shows the arrangement of duplicate busbar system in a typical substation. The two 66 kV incoming lines can be connected to either busbar by a busbar coupler. The two 11 kV outgoing lines are connected to the busbars through transformers, 66/11 of a kV, and circuit breakers. Next we learn about single line diagram of 11 kV substation. The single line diagram of an 11 kV substation is shown in the figure above. The single line diagram makes the system easy and it provides the facilitates reading of the electrical supply and connection. Main components of 11 kV substation. The working of the electrical equipment used in the substation is explained below in details. 1. Isolator. The isolator connects or disconnects the incoming circuit when the supply is already interrupted. It is also used for breaking the charging current of the transmission line. The isolator is placed on the supply side of the circuit breaker so that the circuit breaker isolated from the live parts of the maintenance. 2. Lightning arrestor. The lightning arrestor is a protective device which protects the system from lightning effects. It has two terminals, one is high voltage and the other is the ground voltage. The high voltage terminal is connected to the transmission line and the ground terminal passes the high voltage surges to earth. 3. CT metering. The metering CT measure and records the current when their secondary terminal is connected to the metering equipment panel. 4. Step-down transformer. The step-down transformer converts the high voltage current into the low voltage current. 5. Capacitor bank. The capacitor bank consists series or parallel connection of the capacitor. The main function of the capacitor bank is to improve the power factor of the line. It draws the leading current to the line by reducing the reactive component of the circuit. 6. Circuit breaker. The circuit breaker interrupts the abnormal or false current to flow through the line. It is the type of electrical switch which opens or closes the contacts when the fault occurs in the system. The outgoing feeder supplies the input power to the consumer end. Thanks for watching. Subscribe our channel.